Welcome to Chem-1A at Shasta College. This screencast is an introduction to oxidation-reduction reactions. Let's start with an example. Let's observe something and try to explain what's going on. And what we have here is a test tube with a piece of metal in it. It's reasonably obvious that it's copper from the copper-colored appearance. And it has just been placed in a solution that's clear and colorless. We can't tell what it is by looking at it, but it's a silver nitrate aqueous solution. And when we mix these two things together, combine them, it takes a while, but we start seeing fairly quickly a little gray fuzziness appearing on the surface of the copper wire. Over time, that fuzziness gets larger and larger, lots and lots more of it, and then over time the solution itself starts becoming a sort of beautiful clear blue color. Well, what's happening? It turns out, maybe not too surprisingly, that this sort of silvery gray colored fuzz on the surface of the copper is in fact silver metal, and the blue color is due to the appearance of the copper 2+ ion, and the solution starts becoming a copper nitrate solution rather than a silver nitrate solution. Now, what happens is the copper metal reacts with the silver ion from the silver nitrate solution to make copper ions, Cu2+, and silver metal. And the NO3-, in fact, is a spectator ion, so we're not going to write it as part of this reaction. Now, this reaction is an example of what's called an oxidation-reduction reaction, and the details are as follows. If you look at the copper starting as a neutral atom, becoming a +2 charged ion, that happens when copper loses electrons. And the term chemists use for losing electrons is we say the copper was oxidized. Now the silver starts as a silver positively charged ion, forms the silver metal atoms that are neutral, and for silver ions to become silver metal, they must gain electrons, and the term chemists use for gaining electrons is we would say the silver ion is reduced. I know that sounds like kind of a weird term to use for gaining, but there's a historical reason for that. More on that perhaps later, but for now you just have to accept that chemists say that losing electrons is oxidation and gaining electrons is reduction. Okay, now another thing to note about this reaction is that the copper loses 2 electrons to become the copper 2+ ion, but the silver ion appears to only gain 1 electron to become silver metal. And we can't have electrons just disappear, or for that matter, appear out of thin air. And so, of course, what must be the case is the electrons that are gained and the electrons that are lost have to be equal to each other. If copper loses 2 electrons, they're not really lost. They're gained by something else, in this case the silver. And since an individual silver ion gains 1 electron to make silver metal, we must have, for a gain of 2 electrons, we must have 2 silver ions, each gaining 1 electron to make 2 silver atoms. So we now have a balanced net ionic equation for this oxidation-reduction reaction. Now, if we look at things on a molecular or atomic level, what happens is at the surface of the piece of copper, so here are some copper atoms represented by the copper-colored spheres, and they have some silver ions in solution outside of it. And when some silver ions get close to a copper atom, what can happen is the copper atom can lose an electron, or actually transfer electron, to a silver ion nearby, transfer a second electron to a second silver ion nearby. The copper then forms a copper 2+ ion, and it goes out into solution, and then 2 silver atoms are formed, and they start sticking to the surface of the copper. And over time, more and more and more of this happens, and so over time there's less and less copper underneath, more and more silver on the top, and then gradually the solution turns blue because of more and more and more copper 2+ ions present in the solution. And this reaction will take place typically until you run out of one of your reactants. Now, a couple other things to note. The copper is oxidized, and we call it the reducing agent. And this may sound a little confusing. It's easy to get this stuff backwards, but the thing that is oxidized had to lose electrons to be oxidized. And those lost electrons can be gained by something else, and when something else gains electrons, it's reduced. So in a sense, the copper is helping something else be reduced while it is itself being oxidized. And then, very similarly, but opposite, the silver ion is reduced. It therefore helps something else be oxidized, and so it is the oxidizing agent. And this will be true in general. The thing that is oxidized will be the reducing agent. The thing that is reduced will be the oxidizing agent. Now, you might say, well, that's kind of a cool reaction, but why do we care about oxidation-reduction reactions in general? And it turns out oxidation-reduction reactions are all over the place, a huge part of chemistry and, in fact, life. One of the most common types of oxidation reduction is rusting, but also on a more productive level, all batteries operate under the principles of oxidation reduction reactions. So your cell phone and laptop and iPad and all of your devices that depend on a battery, they run because of an oxidation reduction reaction, as do all kinds of biochemical processes like photosynthesis and aerobic respiration, and maybe you've heard of the Krebs cycle and things like that. These are fairly complicated multi-step oxidation reduction processes, but oxidation reduction nonetheless. And even electric eels operate via little electrochemical cells, physiological cells, that can stun prey with electric current. So, a couple things to note about oxidation reduction. If you're part of the cool in crowd, you can call it redox for short. And oxidation is losing electrons. Reduction is gaining electrons. And it's really easy to get this backwards, so it's always good to have some sort of a mnemonic device or some way of remembering. And there's different ways to do this. My suggestion is always remember that Leo the lion says grr. Leo is lose electrons oxidation, grr is gain electrons reduction. So maybe that'll help you remember and keep it straight. Okay, one more example. This is a reaction you may have seen. Magnesium will burn with oxygen to make magnesium oxide, the ionic compound, and it possibly helps a bit if we write this as Mg2 plus and O2 minus attracting each other. Normally we don't write the formula that way, but this is to sort of make explicit that this is now an Mg plus 2 ion and an oxide minus 2 ion. And now we notice what happened to the Mg. Well, it had to have lost 2 electrons to go from Mg solid to Mg2 plus. Therefore, the Mg is oxidized, and the other substance, oxygen, went from neutral to a minus 2 ion. Oxygen was therefore gained 2 electrons, and therefore was reduced. And then the thing that's oxidized, magnesium, is the reducing agent. The thing that's reduced, oxygen, is the oxidizing agent. And so here we have magnesium and oxygen reacting to make magnesium oxide, another example of an oxidation reduction reaction. A couple things to note. Elements that are likely to be oxidized, well, think about what happens when something's oxidized. It needs to lose electrons, and it's therefore a good reducing agent. And elements that are likely to lose electrons tend to be things over here, like the alkali metals, lithium, sodium, potassium, etc. And the alkaline earth metals, these guys tend to lose electrons pretty easily. They make positively charged ions. In fact, lithium is an important component of a lot of batteries, and it typically functions by being easily oxidized. Now, sort of conversely, elements that are likely to be reduced, and therefore make good oxidizing agents are things that are good at gaining electrons, and they tend to be more on the right side of the periodic table. So the halogens, for example, fluorine or chlorine or bromine, are pretty good at gaining electrons and being reduced. Similarly for oxygen and sulfur, etc. So this part of the periodic table tends to have elements that are more likely to be reduced. Now, a bit of a summary and some general rules. A species or a substance is oxidized, as we've seen, if it loses electrons. And something is reduced if it gains electrons. That's essentially the definition of oxidation and the definition of reduction. Now, this is always going to be true, but sometimes there are like shortcuts or easier ways to see it. A substance is oxidized if it gains oxygen. That is actually where the term comes from. Therefore, it's reduced if it loses oxygen, and that's the actual origin of the term reduction. It comes from having a metal ore, like an iron oxide or something, that you want to purify and get pure iron. And if you get rid of or lose the oxygen, then you reduce it to the pure metal. So that's where that historic term comes from. It turns out also that when a substance loses hydrogen, that generally corresponds to oxidation. And when it gains hydrogen, that generally corresponds to reduction. And those of you who take organic chemistry will use this way of looking at things sometimes. And then one more general one, which we'll talk about in a bit, is there's a concept that chemists use called oxidation number. And if a substance or a species increases its oxidation number, that means it's oxidized. And if it decreases its oxidation number, that means it's reduced. And we'll have more on that in a future screencast. So that's it for the introduction to oxidation-reduction reactions.